The Beer-Lambert law tells us how much light a solution absorbs. A equals epsilon BC, where A absorbance is a number that tells how dark the beam looks after passing through the sample. It is defined as A equals negative log 10 of I over I naught, where I naught is the intensity of the light entering the cuvette, and I is the intensity that comes out. Epsilon, molar absorptivity or extinction coefficient, is a property of the chemical at a particular wavelength. Think of it as how greedy the molecules are for photons of that color. B is the path length, the distance the light travels through the liquid, usually expressed in centimeters. Imagine a tunnel. The longer the tunnel, the more chances the light has to be absorbed. C is the concentration of the absorbing species in moles per liter, More molecules means more opportunities to catch photons. The law says the three factors multiply together. Double the concentration or double the path length, and the absorbance doubles. This simple product is the foundation for almost all quantitative UV-Vis work. The Beer-Lambert relationship can be derived by looking at a thin slice of solution of thickness dx. If the intensity entering the slice is I, a tiny fraction of it, di, is absorbed. di equals minus kc I dx. Here k is a proportionality constant that becomes the molar absorptivity epsilon after we convert units. Rearranging and integrating from the front face, x equals 0, I equals I0 to the back face, x equals b, I equals I. Integral of di over I equals minus kc. Integral of dx leads to ln of I over I0 equals minus kcb. Changing the natural log to base 10 gives the familiar form. Minus log 10 of I over I0 equals open parenthesis k divided by 2.303 close parenthesis bc equals epsilon bc. Assumptions that make the derivation valid. Monochromatic light, the wavelength does not change while passing through the cell. Homogeneous solution, concentration is the same everywhere. No scattering, only absorption removes photons. Reflection or scattering is negligible. No chemical change, the absorbing species does not react or associate as the light passes. Linear response, each molecule absorbs independently. No interaction between absorbing molecules. Limitations arise when any assumption breaks down. At very high concentrations, the solution becomes crowded. Molecules interact and the effective path length shortens, inner filter effect. Stray light from the instrument adds extra photons, making the measured absorbance lower than true. If the light source has a broad bandwidth, different epsilon values across the band blur the result. Chemical equilibria, for example acid-base or complex formation, can change the absorbing species concentration with wavelength. When these conditions are present, the plot of a versus C deviates from a straight line, and the law no longer gives accurate concentrations. Epsilon, the Greek epsilon, is called molar absorptivity or extinction coefficient. It tells how strongly a particular molecule absorbs light at a specific wavelength. Definition: epsilon is the absorbance of a 1 molar solution measured in a 1 centimeter cuvette. In other words, if you place a solution that contains exactly 1 mole of solute per liter in a cuvette that is 1 centimeter thick, the absorbance you record at that wavelength is epsilon. Units: the SI-compatible unit is liters per mole per centimeter. Some textbooks write it as m inverse centimeter, where m equals moles per liter. How to determine epsilon? Step 1. Prepare a series of standard solutions with known concentrations. For example, 0, 2, 4, 6 micromolar. Step 2. Measure the absorbance of each at the wavelength of interest, using a 1 centimeter path length cuvette. Step 3. Plot absorbance A versus concentration C. The slope of the straight line fit equals epsilon times b. Since b equals 1 centimeter, the slope directly gives epsilon. Step 4. Verify that the line passes through the origin. A non-zero intercept indicates stray light or instrument error. Practical analogy: think of epsilon as the stickiness of a door. A very sticky door, large epsilon, will let almost no one pass, high absorbance, while a slick door, small epsilon, lets many people through, low absorbance. The stickiness depends on the color of the door, wavelength. Some doors are sticky only for red light, others for blue. In an ideal world, absorbance grows linearly with concentration forever. In practice, the linear dynamic range is limited. typically from about 10 to the minus 4 to 1.0 absorbance units for most modern spectrophotometers. Stray light that bypasses the monochromator reaches the detector. It adds a constant background, causing the measured absorbance to be lower than the true value, especially when the true absorbance is high, greater than 1.5. High concentration inner filter effect. At concentrations above about 10 to the minus 3 molar, molecules begin to shadow each other. The effective path length is shorter and the relationship becomes sublinear. Scattering also becomes significant. Chemical equilibria. If the absorbing species participates in an equilibrium that shifts with concentration, for example dimerization, 2 irreversibly forms a 2, the amount of monomer A that actually absorbs light does not increase proportionally to the added total concentration. Instrument bandwidth. A wider bandwidth mixes photons of slightly different lambda, each with its own epsilon. The recorded absorbance is an average flattening steep regions of the spectrum. Refractive index changes. Very concentrated solutions change the cuvette's refractive index, altering the beam's path and causing deviation. Stray light is like a flashlight with a cracked lens. Even when you point it at a black cardboard, a faint glow leaks around the cracks, making the cardboard look brighter than it truly is. Inner filter is similar to trying to see through a crowded crowd. When only a few people are standing, you can see straight through, but as the crowd thickens, your view is blocked and you cannot simply count people linearly. To stay inside the linear range, analysts often dilute samples so that the absorbance falls between 0.1 and 0.8 absorbance units, where the instrument is most accurate. Explanation: a calibration curve is a graph that links known concentrations to measured absorbances. Once built, you can read off the concentration of an unknown sample. Steps to construct a calibration curve: Number 1. Choose the wavelength where the analyte has its maximum absorbance, lambda max. This gives the highest epsilon and therefore the best sensitivity. Number 2. Prepare standards: at least 5 solutions spanning the expected concentration range. For example 0, 2, 4, 6, 8 micromolar. Number 3. Measure absorbance of each standard in the same cuvette, same path length, and under identical instrument settings. Number 4. Plot absorbance y-axis versus concentration x-axis. Use linear regression to obtain the best fit line, A equals mc plus b. The slope m equals epsilon b. For a 1 centimeter cuvette, m is approximately epsilon. The intercept b should be close to 0. A significant intercept indicates systematic error, for example stray light or baseline drift. Number 5. Validate the linearity by checking the correlation coefficient, r squared. Values greater than 0.998 are usually acceptable. Number 6. Determine unknown. Measure the unknown's absorbance A sub u, then solve for concentration. C sub u equals open parenthesis A sub u minus b close parenthesis divided by m. Interpretation example: suppose the line equation is A equals 0.025 C plus 0.003 C in micromolar. An unknown sample gives A equals 0.128. Plug in C equals open parenthesis 0.128 minus 0.003 close parenthesis divided by 0.025 equals 5.00 micromolar. The calibration curve also supplies the limit of detection, LOD, and limit of quantification, LOQ, using the standard deviation of the blank sigma blank. LOD equals 3 sigma blank divided by m, LOQ equals 10 sigma blank divided by m. These metrics tell you the smallest amount you can reliably detect or measure. Example 1. Find concentration. A 1.0 centimeter cuvette contains an unknown solution. At lambda equals 450 nanometers, the measured absorbance is A equals 0.650. The molar absorptivity of the solute at this wavelength is epsilon equals 2.5 times 10 to the 4 liters mole inverse centimeters inverse. A solution: A equals epsilon times b times c, therefore c equals A divided by epsilon times b. Insert the numbers. B equals 1 centimeter. C equals 0.650 divided by 2.5 times 10 to the 4 times 1 equals 2.6 times 10 to the minus 5 moles per liter equals 26.0 micromolar. Example 2. Determine epsilon from a calibration. You prepare 5 standards of a dye with concentrations 0, 5, 10, 15, and 20 micromolar. Their absorbances at 620 nanometers, B equals 1 centimeter, are 0.000, 0.126, 0.251, 0.376, and 0.503 respectively. 1. Plot A versus C and fit a straight line. The regression gives a slope m equals 0.0251 absorbance units per micromolar and intercept approximately 0. 2. Convert the slope to epsilon. Remember, 1 micromolar equals 1 times 10 to the minus 6 moles per liter. Epsilon equals m divided by b times 10 to the minus 6 equals 0.0251. Divided by 1 times 10 to the minus 6 equals 2.5, 1 times 10 to the 4 liters per mole per centimeter. Thus, the dye's molar absorptivity at 620 nanometers is 2.5 times 10 to the 4 liters per mole per centimeter. Example 3. Find path lengths. A solution of known concentration C equals 2.0 times 10 to the minus 4 molar gives an absorbance A equals 0.840 at lambda equals 280 nanometers. The molar absorptivity is epsilon equals 4.0 times 10 to the 3 liters per mole per centimeter. Solve for B. B equals A divided by epsilon times C equals 0.840, divided by 4.0 times 10 to the 3 times 2.0 times 10 to the minus 4 equals 0.840, divided by 0.8 equals 1.05 centimeters. The cuvette path length is therefore about 1.05 centimeters, often a 1 centimeter cuvette with a slight alignment error. When a mixture contains 2 or more species that both absorb at the same wavelength, the total absorbance is the sum of the individual contributions. A total lambda equals epsilon 1 lambda times b times c1 plus epsilon 2 lambda times b times c2 plus ... If you measure the mixture at 2 different wavelengths where the relative absorptivities differ, you obtain a set of simultaneous linear equations that can be solved for the unknown concentrations. 2-component example. Suppose species X and Y both absorb at 400 nanometers and 450 nanometers. At 400 nanometers, epsilon X equals 1.2 times 10 to the 4 liters per mole per centimeter. Epsilon Y equals 3.0 times 10 to the 3 liters per mole per centimeter. At 450 nanometers, epsilon X equals 4.0 times 10 to the 3 liters per mole per centimeter. Epsilon Y equals 1.5 times 10 to the 4 liters per mole per centimeter. The path length B equals 1 centimeter. The measured absorbances of the mixture are: a 1 at 400 nanometers equals 0.720, a 2 at 450 nanometers equals 0.690. Set up the equations. 0.720 equals 1.2 times 10 to the 4 cx plus 3.0 times 10 to the 3 cy. Equation 1. 0.690 equals 4.0 times 10 to the 3 cx plus 1.5 times 10 to the 4 cy. Equation 2. Solve by matrix method or substitution. Multiply equation 1 by 4 and equation 2 by 12 to eliminate cx. 2.880 equals 4.8 times 10 to the 4 cx plus 1.2 times 10 to the 4 cy. 8.280 equals 4.8 times 10 to the 4 cx plus 1.8 times 10 to the 5 cy. Subtract the first from the second. 5.400 equals 1.68 times 10 to the 5 cy, gives cy equals 3.21 times 10 to the minus 5 molar. Plug back into equation 1's. 0.720 equals 1.2 times 10 to the 4 cx plus 3.0 times 10 to the 3 times 3.21 times 10 to the minus 5. 0.720 equals 1.2 times 10 to the 4 cx plus 0.0963. 1.2 times 10 to the 4 cx equals 0.6237. Gives cx equals 5.20 times 10 to the minus 5 molar. Thus, the mixture contains 52 micromolar of X and 32 micromolar of Y. General procedure for N components. Step 1. Choose N wavelengths where the set of epsilon values for the components forms a non-singular matrix, determinant not equal to 0. Step 2. Measure absorbance at each wavelength. Step 3. Write the matrix equation A equals EC, where A is an n by 1 vector of absorbances, E is an n by n matrix of molar absorptivities, and C is the unknown concentration vector. Step 4. Solve for C using C equals E inverse times A or linear algebra solvers. Modern software such as Excel, MATLAB, Python can perform the inversion quickly, making multi-component UV-Vis analysis routine in industrial quality control. Explanation below are 5 typical examination-style questions on the Beer-Lambert law together, with the key points examiners look for in the answer. Question 1. State the Beer-Lambert law and define each term. Scoring 2 marks, correct equation A equals epsilon BC. 1 mark each for definition of A, epsilon B. C. Full credit requires the log definition of absorbance as negative log 10 of I over I sub 0. Question 2. A 1 centimeter cuvette contains a solution with epsilon equals 1.5 times 10 to the 4th liter mole to the minus 1 centimeter to the minus 1. The measured absorbance at 540 nanometers is 0.300. Calculate the concentration of the solution. Scoring 1 mark for rearranging to C equals A over epsilon B. 1 mark for plugging numbers. 1 mark for correct answer 2.0 times 10 to the minus 5 molar. Question 3. Explain 2 reasons why Beer-Lambert law may fail at high concentrations. Scoring 2 marks, each reason worth 1 mark. Acceptable answers: inner filter effect, self-absorption, stray light, chemical equilibria shifting, scattering, deviation due to refractive index change. Question 4. A mixture of 2 dyes gives absorbances a sub 1 equals 0.450 at 400 nanometers, and a sub 2 equals 0.380 at 500 nanometers. The molar absorptivities liter mole to the minus 1 centimeter to the minus 1 are epsilon sub 1 400 equals 2.0 times 10 to the 4th, epsilon sub 1 500 equals 5.0 times 10 to the 3rd, epsilon sub 2 400 equals 1.0 times 10 to the 3rd, epsilon sub 2 500 equals 1.5 times 10 to the 4th. Path length equals 1 centimeter. Determine the concentrations of the 2 dyes. Scoring 4 marks, 1 mark for writing 2 equations, 1 mark for solving showing elimination or matrix, 2 marks for correct numerical concentration C1 approximately 2.0 times 10 to the minus 5 molar, C2 approximately 1.8 times 10 to the minus 5 molar. Partial credit for correct setup. Question 5. You prepare a calibration curve for a metal ion at its lambda max. The regression line is A equals 0.042 C plus 0.005 C in micromolar. The blank gives a standard deviation of 0.002 absorbance units. Calculate the limit of detection, LOD, and limit of quantification, LOQ. Scoring 3 marks. 1 mark for formulas LOD equals 3 sigma over M, LOQ equals 10 sigma over M. 1 mark for substituting sigma equals 0.002, M equals 0.042. 1 mark for presenting numerical LOD approximately 0.14 micromolar and LOQ approximately 0.48 micromolar. Exam tips: Bullet point: write the equation clearly before substituting numbers. Bullet point: keep units consistent, convert micromolar to molar if needed. Bullet point: state any assumptions, monochromatic light 1 centimeter path. Bullet point: for multi-component problems label each equation and show at least 1 step of elimination. Bullet point: mention sources of error when asked to explain deviations.